Hi, my name is Ksenia, and today I'm going to present to you our work, Semi-Supervised Reward Learning for Offline Reinforcement Learning. In this work, we're interested in applying deep RL to realistic domains, such as robotic manipulation. However, deep RL requires a lot of data and precise reward signal, which are often not readily available in practice. Thus, in this work, we propose to use offline reinforcement learning with learn-reward functions. In particular, we focus on learning from limited human supervision to minimize the human efforts put into reward learning. As often done in offline reinforcement learning, we start with a big pre-recorded dataset of trajectories. Then, in addition to this, we provide a few demonstrations and optionally annotate them with time-step level rewards. Using the annotated data, we learn the reward function, which is then applied to the unlabeled data to produce reward signals for offline reinforcement learning to learn a policy for the robot. In this work, we are interested in two types of reward supervision: episode and time-step level labels. In both cases, we start with a set of episodes without any rewards associated with them. For the episode level labels, we are given the annotations of success on the episode level, that is, a set of demonstrations without rewards. For the time-step level labels, we provide more detailed time-step annotations of the demonstrations that are given to us. So, we start with a number of episodes when some of them are identified as the demonstrations. Please check the related work ORIL that deals with the same setting. In this work, we are using the time information to guide our reward learning. In particular, we notice that usually in the demonstrations, the task is not solved in the first half of the episode, but it is solved in the second half. Thus, we assign a pseudo-rewards of 0 to the first half of the episode, that is identified as a demonstration, and reward 1 to the second half. The rest data that is unlabeled gets reward 0 assigned to this, and then we train a classifier to distinguish between successful and failed trajectories. We call this approach the time-guided reward. We test it in 4 robotic manipulation tasks, and we use critic regularized regression as an offline RL algorithm of our choice. We provide around 300 demonstrations. Without going into details, our proposed method can match or outperform the results of other baselines. We also notice that if no learning for the reward functions is used, the results are not very encouraging, but they are improved a lot by incorporating unlabeled data and closely approach the performance of policies learned from ground truth reward supervision. Now suppose that we are given a very limited amount of demonstrations, and to compensate for their scarcity, we decide to annotate them with the time-step level rewards. Then we can ignore the rest of the data and train a classifier as we did before. Going forward, we can decide to incorporate unlabeled data again and assign the flat 0 reward to it. In our experiments, we are given around 30 demonstrations only with the time-step level rewards for them. Our main conclusion is that incorporating unlabeled data improves the results significantly and outperforms by a large margin using only labels provided by a human, while both methods have the same annotation cost for the human labeler. Finally, we analyze our results, and here I'll give you a glimpse into a few of our findings. We looked at the connection between the reward model quality and offline RL policy performance. We noticed that they are correlated. However, RL training seems to be quite forgiving to the imprecisions in the reward functions. We also noticed this in our comparison of CRI against D4PG, where CRI shows to be much more robust to this noise in the reward signals. To conclude, we're able to learn offline RL policies with learn-reward functions using only limited amount of supervision, either in the form of episode or time-step level annotations. We also analyze the connection between the reward models and offline RL policy performance, and we have provided a few insights into this. Thank you for your attention.